What is up, guys? What's up? So, what's on the agenda for today? Okay, let's cover some basics. Okay, agenda for today, very simple. We have to prepare for midterms that we have tomorrow. So what that means is tomorrow I have a solid state physics midterm. I should make some tea. We'll do that after we go over this. So tomorrow I have a solid state physics midterm. So what am I going to do today? Well, you better believe I'm going to be studying solid state physics. So we're going to do that. A hard limit is 6 p.m. because then I have a discussion for solid state physics, and then after that we're just going to go to sleep so we can get a full night's rest of sleep. So we're going to cover all that we need to study right now. And then tomorrow we have... So tomorrow is is solid state physics midterm. The day after tomorrow, so Friday, is quantum mechanics midterm. So what we're going to do today is completely review solid state physics. Probably not even worry about quantum mechanics right now, even though we probably should. I need to study a lot for that, actually. But boy, oh boy. Let's check our calendar. Yeah. Well, yeah, tomorrow shouldn't be bad. Shouldn't be bad. So today we study solid state until 6 p.m. Tomorrow we study quantum mechanics until friggin' 10 p.m. Who knows? And then Friday we take quantum mechanics, and then Tuesday we have real analysis. So, you know what? This is what it is, but what we're gonna do. So right now, I'm gonna make some tea. Okay, you're gonna see me make it in that old microwave with the pizza box on top of it. Yes, I know what you're thinking. And it's true. Green tea. The lighting in here is pretty weird. It's a cloudy day today, so lighting is pretty weird. Also, my head hurts, so you know what that means. We're gonna take some ibuprofen for the headache. Not on stream, because I do not want to promote that. You should not. I'm a believer in... Let me drink this. I'm a strong believer in addressing the problem and not ignoring it by putting on a whole bunch of... Basically... I'm a believer in you stop shooting yourself in the foot rather than buying a bunch of Band-Aids, gauze, and hydrogen peroxide to try to clean up every bullet wound that you shoot into your foot. Fix the problem, basically. And the reason why I have a headache, I'm not hydrating enough, and I'm pretty stressed out from studying. But if I were to fix the problem would be fixed by not doing work, dropping out, and that's not an option. So we just gotta buckle up our big boy pants and take a little bit of ibuprofen every now and then, okay? 30 more seconds till that's done. But yeah. Why do I have to live stream myself studying? I'm glad you didn't ask, but I'm gonna tell you. Because before this point, it's 12:40 right now. Before this point, I was just procrastinating, doing nothing. I bought new shoes though, because I need new shoes. My current shoes are like torn up, but. Okay, I think that's long enough. It's quite smoky. You can see that. But okay, all right. Pull the camera back down. Okay. So, switch it back to main. What we're gonna do to study is we're gonna run through again this practice midterm, okay? You've got solutions in another tab right here, but we're not gonna look at them yet. I already ran through this once, but it's good to run through it again just to cement all ideas. And yeah, we're gonna, ask ChatGPT, hey, can you explain these things? If the solutions don't really make too much sense, etc., etc. After we run through this practice midterm again, we only have like 3 homeworks to look through for solutions, so we'll do that. We'll look through these 3 homeworks, February 9th, yeah. So there's 3 homeworks with solutions as well, so we'll look through that as well. And that should cover all of it. Homework 1 was chapter 3, homework 2 was chapter 4, homework 3 was chapter 2. Right? Yeah. So this should cover pretty much all of our bases. Bonus points, we go back to chapter 2 and 3 and we read them. That's bonus points though. Honestly, I don't think we need to reread chapter 3. I think we have a pretty decent understanding of what's happening in chapter 3. Maybe not, actually. I think I ignored this part. But we'll just read the chapter summaries, I guess. Worst comes to worst. But yeah. So, let's start with looking at midterm 1. Okay, the practice exam for midterm 1. Let's get out a piece of paper. I have a piece of paper here. You can't see it. Well, now you can. I have a piece of paper here. This is the current desk setup. Okay, piece of paper right there. So, let's jump right into it. First of all, we need some background music, background noise. This is not going through my mixer. Now it is. And now you can hear it. Okay. So. Bloop, 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 bloop. Blue, 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 blue. I'm blue. Okay. I think the first problems are kind of just a walkthrough. So number 1 is kind of walkthrough. Number 2, you could walk through it, but also there's equations to it. Number 3, there's equations to it. And number 4, partially walkthrough, partially equations. So let's talk through this. Number 1, drift velocity. Explain what drift velocity means in the context of the Drude model, okay? So in the context of the Drude model, what the drift velocity is it's basically the average velocity of all of the electrons that are moving around inside of a material. That's on a broad scale what you would call drift velocity. So in the context of the Drude model, in relation to what's actually going on, so when we look at materials, when we look at electrons in a material, we think of them as existing in something called K-space, okay? And K-space is basically a graphical representation of the momentum eigenstates that electrons can occupy, I think. I think it's momentum eigenspace. What is K-space in relation to solid state physics and their relation to electrons in a material? Yes, momentum space. Quantum states of electrons within a crystal lattice. Okay, so each point in k space represents a wave vector k, which corresponds to the momentum of an electron within a solid. So the wave vector is a fundamental concept in quantum mechanics and solid-state physics, embodying both the direction and the wavelength of wave-like particles, such as an electron, in a periodic potential. Okay, so wave vector k describes the direction and magnitude of a periodic wave in the context of electrons and solids, blah, 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 blah. Each point in k space corresponds to a specific energy state of an electron, based on the relationship between the electron's energy and its wave vector. This relationship is depicted in the band structure. So I was right. Okay. So I was studying with a friend yesterday, and I was like, k space basically represents all the energy states an electron can occupy. And he was like, well, technically it's momentum space, but momentum is related to energy, because when you talk about k space, yeah, okay. So k space, each point in k space corresponds to a specific energy state of an electron, because there's a relationship between an electron's energy and its wave vector E of k. Yeah, makes sense. Yeah, okay. So going back to this problem, right? Going back to this problem, drift velocity, basically, you can think of it as when you look at a material in k space, when you analyze things in k space, right? Each point in k space represents an energy state of an electron, and when you take the energy state at temperature, at zero temperature, right? The highest energy state, you can draw some sort of circle around that, draw a surface around the highest energy state, and that gives you a Fermi surface. And with that Fermi surface, what it basically represents is what does a Fermi surface represent? What does a Fermi surface represent, actually? Highest occupied electron energy levels, yeah. Well, yeah. Okay, so the Fermi surface represents the highest energy occupied levels within a material. And when you have this material in the presence of some external field, it'll shift this Fermi surface in a particular way. And the velocity of the shifting of this entire Fermi surface is what drift velocity is. So drift velocity is not some measure of the velocity of electrons, individual electrons that are moving within a material. It is the average velocity, the mean ensembled average velocity of electrons that are in a material. That's what the drift velocity is, basically. And then B, the average kinetic energy of an electron in a Fermi gas model is larger than that of a classical gas by a factor of about TF over T. Explain why the Drude model still gives good predictions for the conductivity of a metal. Well, for the conductivity of a metal, the Drude model overshoots the temperature and also undershoots by like a factor of 100 or something like that, right? I have this written down. I think it's page 32 in the textbook. It's somewhere here. Yeah, Drude theory predicts a factor that is larger by a factor of 100 yeah, the CV, so the specific heat the Druta uses is larger by a factor of TF over T, but the expectation value for the velocity squared is too small by roughly the same factor. So yeah, so the specific heat is overshot by a factor of 100, but drift velocity is also undershot by a factor of 100, so then it balances out, just about. But yeah. And it also gives a good prediction for the conductivity of a metal, because conductivity in the Druta model doesn't really take into account quantum mechanical effects, I think. I don't really quite know the answer, actually. Although the average kinetic energies of electrons in the Sommerfeld model are much higher than those in the Druta model, the average velocities under an applied field are the same. Yeah, the spherical Fermi C is centered at k equals 0, and the center of mass... Okay, what? So drift velocity is the average velocity of all electrons in the gas. Note that the drift velocity is 0. If there is no applied electric field, the electrons will still have some non-zero. Okay, yeah. Okay, so my explanation for A is pretty much the same as the explanation for B. What? Although the average kinetic energies of electrons in the Sommerfeld model are much higher than those in the Druta model, the average velocities under an applied electric field are the same. The spherical Fermi C is centered at k equals 0, and the center of mass of the gas has 0 momentum. Under an applied electric field, the Fermi C shifts slightly to be centered at some k drift. Yes? Then V drift equals h bar k drift over m is the same as the velocity v that appears in the Druta equation of motion. Equivalently, we could say that in the Druta model, all of the electrons participate in scattering. In the Sommerfeld model, although the electrons are moving much faster, only a small fraction of them participate in scattering. Ah, okay. Okay. For the conductivity of a metal, yeah. So the Druta model sees it as all electrons on average are participating in scattering. However, in the Sommerfeld model, okay, wait. So although the average kinetic energies of the electrons in the Sommerfeld model are much higher than those in the Druta model, the average velocities under an applied electric field are the same. Okay. Okay. So in the Druta model, it gets conductivity right because it assumes that all electrons are moving at some average velocity. So even though that it assumes that all electrons are involved in the scattering process, it also undersells the velocity of all of those electrons by a lot. So it balances itself out because in the Sommerfeld model, we see that electrons are actually moving much, much faster. However, there are a lot fewer electrons that can participate in the scattering event because when you look at K-space, only the electrons that are near the surface of the Fermi sphere are allowed to change their energy levels. So they're only the ones at the surface are allowed to scatter. So there are now much fewer electrons that participate in this, but actually the ones that are scattering near the surface of the Fermi level are scattering much, much faster. So it balances itself out in the Druta model. Because even though we assume now that all of the electrons within this Fermi sphere are contributing to it, their drift velocity is now like much, much, much lower. Yeah. Or the velocity is much, much lower. Okay. So the drift velocity is just the average movement of all the electrons in a metal. Okay, yeah. I need to ask if the explanation for A, explaining that drift velocity is the movement of the Fermi sea or whatever, is the same as the answer for B. I don't think it's the same as the answer for B, because the answer for B is not just talking about the drift velocity, but it's talking about the electrons that are on the surface of the Fermi sphere and how they contribute to scattering, versus how in the Drude model it doesn't have that picture, but it still works out because it assumes that the velocities of the electrons are much, much less than they actually are. And it also assumes, because the Drude model assumes that all electrons are participating, you would think that it would hella overshoot it, but the velocity is also, they also predict the velocity to be much less, so then it doesn't actually overshoot, it ends up being like a pretty good guess. So Drude model is a pretty good guess, but it's not how it works. Wow. Okay. Magnetism. You measure the Hall coefficient of a metal to be RH equals 0.5 angstroms cubed over electron. Could you have predicted this Hall coefficient from the Drude model? So, you know that RH is equal to 1 over NE, I think, or NQ. And Q in this case is equal to negative E, so this is negative 1 over N over 1 over E. And so already you have a negative sign in here. So the negative sign would make it so that this is incorrect. However, 0.5 angstroms cubed on that order, would it still be a good guesstimation? Because N is equal to N over V. So this is equal to V over N. Number of electrons, 1 over E. N over V is about 10 to the negative 23, I think. This would be 10 to the negative 23, negative 1 over E. And since E, I can't do dimensional analysis. But I think for this one, I remember the answer for last time, so this is kind of cheating. But, so this would be a no. But let's ask ChatGPT, actually. Let's see what it says. It's always good to get more info. Answer this and explain your reasoning. Dude, the guy's name was Paul? Maybe I should get a PhD in physics. Okay, it's giving me a long PR answer, which I appreciate, but in the Drude model, the Hall coefficient for a charge Q is given by that, and we would always predict a negative Hall coefficient with the Drude model. Okay. So basically it just has to do with the negative sign. The fact that this Hall coefficient is 0.5 angstroms. Okay, but I would have to ask, is the order of 0.5 angstroms, is that predictable? And if so, how? So ask. I have a couple questions that I need to ask, right? 1. Explain the drift velocity. No, I think I've already answered my question for that. So, in 2A, would there be an argument to be made about the order of magnitude of 0.5 angstrom cubed over electrons? Is there another reason why Judah can't predict this coefficient beyond a sign difference? If a magnetic field is applied to a free Fermi gas, there will be an effect on the electron's spin as well as their momentum. In particular, letting up symbolizes a spin that is aligned with the direction of B, and letting down symbolizes an anti-aligned spin. We have that, where mu is greater than 0 is a constant. Given this information, which of the following quantities should be larger for a given E? G up E or G down E? Here, Gs of E is the density of states for the spin state S. Explain your reasoning. So here, up is aligned with the direction of B, so our magnetic field is aligned up. And here, we're just asked, which of the following quantities will be larger? So, which would have more density of states in a B field with spin up? This is what I can't reconcile this with polyparamagnetism. Because polyparamagnetism, right? Magnetic spin susceptibility. What this basically says is that magnetization is in the direction of the applied magnetic field. Yeah. So wouldn't it align itself in the direction of the magnetic field? When the magnetic field is applied, it states with up and down spin are shifted in energy by plus mu BB. Recall that the density of states for a three-dimensional free electron gas goes like the square root of epsilon. In this case, all of the up states are shifted higher in energy so that the new minimum energy achievable for an up electron is that. Magnetization vector. How is it defined again? Does it go from like, where's the head and where's the tail? Yeah, results in a net magnetization that is in the direction of the magnetic field. So what the hell? I just want to see what ChatGPT is going to say. Let me go use the bathroom real quick. I just had the thought I should do like a gym. I should do like a lift, cardio. Monday lift, Tuesday cardio, Wednesday lift, Thursday cardio, Friday lift. Or maybe Monday, Tuesday, Wednesday, Thursday, Friday lift, Saturday, Sunday cardio. Or Monday, Tuesday lift, Wednesday cardio, Thursday, Friday lift, Saturday cardio, Sunday rock climb. Maybe that'll be the split. I think I should do like a split like that or something like that. That'd be cool. But anyways. Okay. In the context of a free Fermi gas subjected to a magnetic field B, the energy of an electron will depend on its spin orientation relative to the direction of B. The energy of an electron with spin up, which is aligned with the magnetic field, is increased by the term mu B. Yeah, so the energy of an electron with spin up is increased by the term mu B, while the energy of an electron with spin down, which is anti-aligned with the magnetic field, is decreased by mu B. Given these energy relations, we need to compare the density of states at a specific energy epsilon for spin up and spin down. For a given energy, the density of states is defined as the number of available quantum states per unit energy range near that energy. The key point here is that the density of states in a free electron gas depends only on the energy of the electrons and not on their spin. This is because without a magnetic field, the energy levels are degenerate with respect to spin. I don't understand that. However, when a magnetic field is applied, this degeneracy is lifted. For a given energy epsilon, more spin down states will be available because the energy of these states is lower due to the subtraction of mu b. Therefore, to reach the same energy epsilon, a spin down electron will have a larger wave vector. Is there an intuitive way to understand the solution for this problem? Dude, I am just mistyping constantly nowadays. I'm trying to understand this, because if you have an electron spinning, you apply a magnetic field, and it's spinning in the direction of the magnetic field, that's going to just increase its energy. So to lower its energy, it's going to want to align itself anti-aligned with it to resist it, to lower its energy, basically. Conservation of energy. That's the most important thing to think about. So if you have magnetization, electron spinning, it's going to want to align itself anti-aligned. I just don't get the argument for that making more energy levels or whatever. Like, I don't get it. Okay, when you apply magnetic field, it's like you're pushing down on one staircase, the spin down staircase, and lifting the other, spin up one. If you choose a particular height and look for the step or the energy state that matches the height on both staircases, you'll find something interesting. For the push down staircase, you'll have to go a step higher to reach the same height, because the whole staircase has been lowered. For the lifted staircase, you'll find the matching step is lower down. Now, if the number of steps is proportional to the height you've climbed, then the staircase that's been pushed down will have more steps at the chosen height because you've climbed higher to reach the same height. Translating this back to the density of states, which is like the number of steps at a particular height, you can see that for the spin down electrons, when the staircase is pushed down, there will be more states available at the chosen energy epsilon compared to the spin up electrons where the staircase is lifted. In this analogy, the number of steps you've climbed correlates with the density of states. So this is not a good analogy, I don't think. Dude, my head is killing me right now. Oh my god. Oh my god. I need to brighten up this webcam. The dark filter needs to be applied. There we go. Now I'm brighter. Look at that. Or I guess not the dark filter, but the filter for when it's dark. It's going to be raining soon? God damn. McDonald's has free delivery. I'm not going to use that. I have food at home. I do need to get dish soap, mayonnaise, and paper towels, though. Those are some things that I need. I do need those. Bruh, it's taking so long to generate. But I guess this would just make sense intuitively, because if you have a magnetic field and the spin is aligned with the direction of the magnetic field, that magnetic field, especially with the spin up, is just going to increase the energy of this, like, infinitely. Degeneracy in the context of quantum mechanics and solid-state physics refers to a situation where two or more different quantum states share the same energy. In the case of an electron in a metal without an external field, the energy of an electron is determined solely by its wave vector k and not by its spin state. Yeah, this means that an electron with spin up and spin down can occupy the same energy level if they have the same wave vector. Thus, each energy level is actually twofold degenerate, one state for each spin orientation. When you apply a magnetic field, the energy levels of electrons are affected by their spins due to the interaction between the magnetic moment of the electrons and the external field. This is known as the Zeeman effect. The energy of an electron in magnetic field B becomes that for spin up and that for spin down. Here, mu is the magnetic moment of the electron, and B is the magnetic field strength. Because of the magnetic field, the previously degenerate energy levels are now split into two different levels depending on the spin orientation. Spin up electrons will have a slightly higher energy because their magnetic moments are aligned with the field, and this alignment is energetically favorable. They will have a slightly higher energy because their magnetic moments are aligned with the field, and this is energetically favorable. Spin down electrons will have a slightly lower energy because their magnetic moments are anti-aligned with the field, which is energetically less favorable. This splitting of the energy levels is a lifting of degeneracy. Each energy level that was previously degenerate now becomes two distinct levels, one for each spin state with different energies. Think of it like a pair of twins that are indistinguishable in a family photo without any context. I don't understand how, because energy of the spin up electrons are increased, that means that the density of states will be with the spin down electrons. Shouldn't it be that the density of states increases with the more energy you have? I guess no, that doesn't make any sense, because density of states is empty states? Bro, you did not answer my question. I guess I could find out the secrets to the midterm by looking at each chapter. So drift velocity, that deals with chapter, I think it deals with chapter, drift velocity is chapter 4? I think so. This is chapter 4. Magnetism is chapter 3. Right? Or is that, no, magnetism is chapter 4. Electron dispersion is chapter 3. And then non-uniform sound speeds is the Debye model. So this is chapter 2. So I can just look at everything that is not covered in the practice midterm, and that will probably be guaranteed to show up on the midterm. So we'll do that after this, actually. Blue, 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 blue. I need to lose weight again, man. My face fat is getting a little out of control. I just see an old picture of me. Bro. So much less face fat than now. It's crazy. That's crazy. Anyways, I need to turn on the light. Can't get cozy. You need the sterile white light. Okay. To address your question, let's first clarify what the density of states means. The density of states at a certain energy level is the number of available electron states at that energy per unit volume. It is not about having more energy, but about how many states are available for the electrons to occupy at a specific energy. In the absence of a magnetic field, each energy level can be occupied by two electrons, one with spin up and one with spin down, due to the Pauli exclusion principle. This is the degeneracy of energy levels with respect to spin. When a magnetic field is applied, the energy levels for electrons with spin aligned with the field increase by mu b. Conversely, the energy levels of electrons with spin anti-aligned in the field decrease by mu b. Now consider a specific energy value epsilon. We want to find out how many states are available at this energy for spin up and spin down electrons. For spin up electrons, because their energy has increased due to the magnetic field, the states that were previously at energy epsilon have now moved up to epsilon plus mu b. So at energy epsilon, there are fewer spin up states than before. For spin down electrons, because their energy has decreased due to the magnetic field, more states have moved down to energy epsilon. Specifically, the states that were previously at energy epsilon plus mu b are now at energy epsilon. So at energy epsilon, there are more spin down states than before. So there's fewer spin up states. Therefore, at a fixed energy epsilon, the density of states have effectively increased because more states have been pulled down to this energy due to the magnetic field. It is not about the energy being higher or lower in an absolute sense. It is about how the application of the magnetic field shifts the energy levels of spin up and spin down electrons, affecting the number of available states at a given energy. Wait, what? Because their energy has increased, the states that were previously at energy epsilon have now moved up. So at energy epsilon, there are fewer spin-up states than before. Okay, so previously, there are some spin-up states at energy epsilon, and then when you apply magnetic field, they move up epsilon plus mu b. So there's fewer, so at epsilon, there's less spin-up states. But at, for spin-down states, so spin down, you look at energy epsilon, there's states that are here, and now in a magnetic field, they move down. I guess. I think this is exactly the reason why, yes. Okay. In a magnetic field, nature does indeed tend to align magnetic moments to minimize the system's energy. However, electrons are fermions and must obey the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state simultaneously. This principle applies regardless of the presence of a magnetic field. In the absence of a magnetic field, each energy state can be occupied by two electrons with opposite spins, and these states are degenerate, meaning they have the same energy. When you apply magnetic field, this degeneracy is lifted. Electrons with spin aligned with magnetic field spin up will increase in energy because the magnetic moment is opposite to the spin direction. By convention, the magnetic moment of an electron is opposite to its spin. Oh shit. The magnetic moment of an electron is opposite to its spin. Ah, fuck. That's the main thing. So when it says like spin down, magnetic moment is actually up. So in a magnetic field, the spin down electron will have a magnetic moment aligned spin up with the magnetic field. That's why. It's because electrons are negative. Oh my god. Now Pauli's paramagnetism susceptibility, whatever the fuck it's called, magnetic spin susceptibility, Pauli paramagnetism. Now it makes sense. Yeah. Okay. Why is aligning its magnetic moment? I guess aligning the magnetic moment with the magnetic field would minimize the energy. Because the spin, we're not thinking a spin. Now, let's say an electron spin is spinning like this, and we have a magnetic field pointing like this. If it kept spinning like this, it would have a shit ton of energy. That would just be too much energy. So, in order to conserve energy, it's going to be like, whoop, it's going to flip down and start spinning down. However, if you look at this picture from magnetic moments, instead you have magnetic moment of an electron is this. And then when a magnetic field is applied, it flips to align itself with the magnetic field. Because that would be less energy. Because the magnetic moment, remember, the magnetic moment, right? It's almost like a dipole. You can think of it like a dipole, and that in a magnetic field, if it were to not point in the same direction as the magnetic field, that would take a lot of energy because it's like, I have to resist being like, like flip. It's like when you bring a magnet to something. When you bring a magnet to something, it'll just want to be attracted to it, but it takes energy to not get it attracted to it. That's the same way the magnetic moment works. Kadoosh, skadoosh, boosh. So now with that newfound insight, let's go back to the problem, right? So up symbolizes a spin that is aligned with the direction of the magnetic field. Down symbolizes an anti-aligned spin. So when the magnetic field is going up, if the spin is up with the magnetic field going up, that will add energy to it. That makes sense. If the spin is down, it'll take away energy for it. So given this information, which of the following quantities should be larger? So the density of states in a magnetic field with magnetic field pointing in the up direction, which is going to have a larger density of states, meaning which is going to have a larger amount of electrons occupying that energy level at that point. And it will be the down ones. Why would it be the down ones? That's the question. Why would it be the down ones? Because the electrons, the energy levels, right? If you look at the energy level epsilon for spin up, all of those spin up. Is it raining? There's someone there, Jesus. All of those spin up electrons. There's someone walking around over there. It's kind of nerve-wracking a little bit. But anyway, I just completely lost my train of thought, but Density of states is a property of the energy levels themselves, not the occupation of those levels by electrons. The density of states tells us how many states are available at each energy level when the magnetic field is applied. The energy of states with spin-up electrons increases, so there are fewer of those states at a given energy. So the energy of states with spin-up electrons increases, so there are fewer of those states at a given... Fewer of those states are available. The energy of states with spin-down electrons decreases, so there are more of those states. This results in an increase in the density of states with energy epsilon for spin-down electrons and a decrease for spin-up electrons. Not because electrons want to be in one state or another, but because the energy levels themselves have shifted due to the magnetic field. So magnetic field is applied, energy levels will shift. Energy levels shift. The fuck? I'm still not getting this picture. I'm not understanding the picture. Too much fucking reading. I'm gonna go pee again. Oh, it is raining. Almost fell. Oh, it's raining quite a bit actually. Yeah. You know, Apple's weather app says that it's light rain. It is not light rain, bro. This is moderate rain. This is moderate rain, dude. But anyway, getting back to it. Let's get right back into the news. Fuck, we've already been streaming for an hour? No way. We've been studying for an hour? There's no shot. No shot we've been studying for an hour. We've been studying for an hour? Yeah, I heard myself, okay? Damn, we kind of have been. That's kind of crazy. Look at our discipline. Look at how disciplined I am. That's kind of crazy. I'm like so disciplined. Okay. Paint me a more intuitive picture of this. First of all, with my newfound knowledge, let's just reread the answer. The density of states for the spin down should be larger. Recall that the density of states for a three-dimensional free electron gas goes like square root of epsilon. In this case, all of the up states are shifted higher in energy so that the new minimum energy achievable for an up electron is mu b. Let's try to work this out from the equations, shall we? Shall we? Yodi gang, shall we? Shall we? So epsilon is equal to h bar squared k squared over 2m plus mu b. So an epsilon minus mu b times 2m, right? Epsilon minus mu b times 2m over h bar squared. Square root is going to be equal to k. Right? Yeah. So those are just some constants. Really, you can pull them out. So instead of 2m, square root of 2m, if you were to square that, I don't know how to think that. But anyway, so it's epsilon minus mu b is k. So an n, which is the density of states, is now going to be equal to L cubed over 2 pi cubed times 4 pi integral of k squared, which is now just 2m epsilon minus mu b over h bar squared dk. Or I guess now you have to take the derivative of k. So then dk would be equal to derivative of k. I don't know what you would take the derivative with respect to here. D epsilon? It's too much. So I guess you just go with that, express it in terms of k, where k is going to be like the energy levels for an electron. Because k is the wave vector. I mean, it makes sense if you do it like that, I guess. Okay, imagine you have a fixed amount of energy to distribute to a group of kids on a playground to climb up a slide. The slide represents an energy level in a material. The amount of energy you give each child determines how high they can climb. Now let's introduce the concept of magnetic field as a strong wind blowing across the playground. Some kids are wearing sails on their backs, and this wind pushes them down the slide, so they can't climb as high with the same energy. Other kids are wearing a special gear that harnesses the wind to help them climb higher. Thus, they can reach higher points on the slide with the same amount of energy they had before the wind. When you apply the wind, the magnetic field, the kids with sails find it harder to climb up to the same height as before. So at a certain height, there will be fewer kids with sails than before because some can't reach that height anymore. On the other hand, the kids with special gear, spin down electrons, can use the wind to climb higher. So at this point, there are now more kids than before because it's easier for them to reach this point with the help of the wind. In this analogy, the height each kid can reach is the energy level of the electrons. The density of states refers to how many kids can reach a certain height on the slide. When the magnetic field is applied, it is easier for spin down electrons, kids with special gear, to reach a given energy level, which means more of them can get to that energy, increasing the density of states for spin down electrons at that energy level. So the key is not that there are more spin down electrons overall, but rather the magnetic field makes more energy states accessible for spin down electrons at a given energy, while the spin up electrons have fewer accessible states at that energy because the field is effectively an obstacle for them. Okay, so if we look at an energy level, that means if we look at an energy level, we have spin up electrons that are occupying this energy level, which means they have a magnetic moment pointing them down. In the presence of a magnetic field, this will take them up higher on the energy level, So at this energy level, there's going to be less of them, less of spin up because they're going to move. But then spin down is going to move down towards it. But then you can just think of the same, you could think of that in another way where like, if I have an energy level that are primarily with spin down, right? And then there's spin up here. Well, I don't get it. That doesn't make any sense. This doesn't make any sense. This doesn't make any sense to me. I don't get it. I don't get it. What are office hours for these people? Solid state physics. What day is today? Today is Wednesday, right? Yeah, it's Wednesday. None of their office hours are on Wednesdays. Great. I can just ask them tomorrow, but I guess this isn't even that huge of a deal, man. It's not. I highly doubt a question like this is going to be on the midterm, man. Like, but let's think about it, okay? Let's think about, how would I answer this? Which of the following quantities should be larger for a given epsilon? G up epsilon or G down epsilon? Well, given that if an electron, so if you apply a magnetic field up, what that would do is that would, I don't even know the picture anymore. I've lost the entire plot. So plus mu b minus mu b, with B activated, the energy level of ones with spin up is going to be increased because it's going to increase their energy. That doesn't even make sense now with my magnetic moment picture. If it's spin down, if you point magnetism, it's going to give it more energy? How is it going to give it more energy? I guess it will give it more energy because it'll now move, right? But if it's already spin up, you apply that, it's gonna, I don't even get it anymore. I completely just gaslit myself into not understanding it. I get this picture, like I get this if you just solve it in terms of K, but what does K represent again? I've thought of another way to think about it. If you solve for epsilon in terms of K, you get some term where epsilon minus mu b remind me, however, what K represents and what its importance is physically. Because K is just a wave vector, right? But what does that wave vector represent? Like, why are we solving in terms of K? Is K the energy? Yes, the wave vector describes both the direction and wavelength, right? Yeah. The energy of the electron in a crystal is given by the relationship between the wave vector K and the energy epsilon. This relationship is described by the band structure. The density of states function depends on the wave vector K because it counts the number of available states at a given energy. The Fermi surface is defined by the set of points in K space that corresponds to the Fermi energy. You can see how changes in energy due to the external. the way that I thought about it before, right, was at B, you have electrons that are spinning up. If you apply a B, if the electron is constantly spinning up, it'll gain more and more energy, or it'll gain more and more momentum, which will increase its energy. So thus, the electron has to spin down, and that would decrease the amount of energy that it's receiving from it. And so since the electron is spinning down, it's decreasing its energy, and since nature wants to decrease energy all the time, then more and more electrons are going to be spinning down. Thus, the density of states for electrons spinning down is going to increase because there's going to be a lot more electrons that are spinning down. That's the bullshit picture that I have in my head. I don't know if that's correct, though. I don't think that makes sense. I don't know what the true picture is, but you know what? We're going to move on. Because I think I spent like a long time thinking about that question, dude. Oh my god. Oh my god, that was a lot. The midterm is tomorrow, bro. What the fuck am I doing? Anyway, number 3. This is one that I really don't know how to answer. So let's try to do it, right? So we know epsilon is equal to A, K, B. G of epsilon is equal to 3 epsilon to the 5/4 over 4 pi squared gamma cubed, right? So now let's start with the equation. N is going to be equal to the volume integral of G, E, D, K. Or is it DE? Is it DE? Fuck, is it GEDE? Did I get it wrong the whole time? It's GKDK. Oh, GKDK. And is this just equal to GEDE? How'd you get this change of variable? How did they change variables to epsilon in this problem? Okay, let's try to do this manually. Let's try to do what it's explaining manually. So we have n. I should use my iPad for this because then I can have it on screen and it'll be better for your viewing pleasure. But I'm not going to do that. So we have n is equal to volume times integral of gk dk. You know that this whatever, this integral is going to just be 4 pi k squared dk from 0 to kf. Right, and now you want to express k in terms of epsilon because your problem is giving you epsilon. So how do we do that? Well, we know that epsilon is equal to h bar squared k squared over 2m. What is k in terms of epsilon? Well, that's just going to be epsilon 2 epsilon m over h bar squared. Square root is going to be equal to k. Right, so we don't even need that. We can just use k squared is equal to that. Right, so we have that. And now we need dk. So to find dk, we would need to take the derivative of this. Which should be 2 epsilon m over h bar squared to the 1/2. You get to dk. Like, I don't know what you would take it with respect to. I guess dE? Yeah, I guess dE. Take the derivative with respect to epsilon? How would you do that? Like, I wouldn't think of that naturally, but I guess I just have to do it. Okay, let's start it over, I guess. Let's start it over. So we have n. So what are we given? Let's go to the problem. Right, this is all we're given. So we're given, so we got to start off with this formula. N is equal to v integral g of epsilon dk, right? So this is going to be v over 2 pi cubed because that's some constant. Times 2. So 2. Why do we times it by 2? Why is there a 2? I guess we just use a 2. So we have some constant of 2 that's also in there. Integral of 4 pi k squared dk. We know that epsilon is equal to h bar squared k squared over 2m, right? So now we want to find k. So we want to express things in terms of epsilon because we're given epsilon in the problem. And we want to figure out, we want to find the dispersion relationship for epsilon. So we need to express things in terms of epsilon so we can figure it out. So it's going to be epsilon 2 epsilon m over h bar squared. It's going to equal to k squared, right? So we have k squared, and now we need to find dk. To find dk, we'll just take dE is equal to h bar squared over 2m k squared d by dk, whatever, which is d epsilon 2 h bar squared over 2m 2k dk. Those twos cancel out, so then you have h bar squared k over m dk is equal to d epsilon. So dk is now just going to be m d epsilon over h bar squared k. So you have dk and you have k squared, so now you can plug this back into n. So n is going to be equal to 2v over 2 pi cubed times the integral of 4 pi k squared, which is going to be 2 epsilon m over h bar squared, times d epsilon, or dk, which is now m d epsilon over h bar squared k. Yeah, m d epsilon. M d epsilon over h bar squared k. All right, and now we crank this out. So 2v over, what's 2 pi cubed? 2 pi times 2 pi is going to be equal to 4 pi squared. 4 pi squared times 2 pi is going to be equal to 8 pi cubed. So it's 8 pi cubed. I guess you could just cube each term individually. Just want to make sure. Over 4 pi times, damn, you guys really can't see this. I guess, now you can get an idea that I'm working this out. You still can't see it, but, you know, it is what it is. 4 pi times 2 epsilon m squared over h bar to the 4 k d epsilon. This will be equal to, so you can cancel that out, 2, 4, 6, 8. That's going to go into it 4 times. That pi is going to cancel, that 4 is going to cancel, so that's pi squared. So now you have, what, 2v over pi squared m squared over h bar 4k dE. But we still have a k here, so we need to express this k in terms of epsilon. Integral of dE epsilon. So k is equal to square root of 2 epsilon m over h bar squared. So let's plug that in. So 2v over pi squared times m squared over h bar to the 4 times 1 over k. So it's going to be k, so then 1 over k is just 1 over that. 1 over the square root of 2 epsilon m over h bar squared. I guess that would cancel out. So if you take out, how do you pull things out of square roots again, dude? If I have the square root of 4, if I were to pull out 4 from the square root of 4, let's say square root of 4 is equal to 2, right? So if I want to pull out the square root, I have to square both sides. And 4 is equal to 2 squared. So I have to take 2 squared. And how would I do that? So I have square root of 4 is equal to 2. I want to take 4 out of the square root effectively. So I would say square root of 4 is equal to something squared. It's equal to x squared. Say square root of 4 is equal to x squared, right? So now if I square both sides, then I would say 4 is equal to x to the 4. No, it's the opposite. It has to be the opposite. Square root of 4 is equal to square root of x. Square both sides. No, it's so dumb. I'm being stupid right now. How do you take things out of square roots? Because if you pull out square root of 2, give you 4? Dude, I'm being so dumb right now. How do you pull things out of square roots? Let's just Google it, I guess. How to pull variables out of square root. If the exponent of the variable is even, divide the exponent by 2 and write the result. What the fuck? There's got to be like an actual way to do this. You factor and do a bunch of shit? What the hell? I can't believe I'm watching this.
In this video, we're going to focus on how to simplify radicals with that's too much, root x. Now, another way you can simplify this or get that same answer is if you 1x. So this will come out as 1x, and this will come out as another x. And you're going to get x times x, square root of 1x, just x by itself. So this is equal to x squared root x. Now, you can simplify this or get that same answer is if you do it this way. How many times does 2 go into 5? 2 goes into 5 2 times, because 2 times 2 is 4. 2 times 3 is 6, that's too much. And what's remaining? 5 minus 4 is 1, so you get 1 remaining. That's another way you can simplify. So let's...
Okay, so let's try that. So square root of Square root of 2 epsilon m over h bar squared. So this is 2. So how much times does 2 go into 1? It can't. So I guess you can't pull it out? What the
For
fuck?
example, if... Now let's try this one. How many times does 2 go into 7? 2 goes into 7 3 times with 1 remaining. Now let's try this one.
2 goes into 7 3 times. 7, 2, 4, 6. So you pull out a 3. You're left with that. So 2 goes into 2 one time. So you pull out 1. Yeah, 2 goes into 8 4 times. So you pull an x to the 4.
2 goes into 8, or 8 divided by 2 is 4. 2 goes into 8 4 times with no remainder. 2 goes into 9 4 times, and 2 goes into 12 6 times with no remainder. For the 9, there's a remainder of 1, so the y is still on the inside. That's a quick way that you can use to simplify radicals. Now let's say if you have a number. Let's say if you want to simplify the square root of, let's say, 32. What you want to do is break this down into an absolute value. Now your teacher may not go over this, but some teacher...
Okay. Bro, I can't believe I'm looking this up, bro. I guess it makes sense though. You have to pull out factors that are perfect squares, right? Basically what I'm trying to work out, it doesn't even have it here. Well, square root this, and I'm trying to work out that step, but anyway. 2v over pi squared times m squared over h bar to the 4 times h bar, because I know I can at least pull out an h bar, over square root of 2 epsilon m. So now that's over 2 epsilon m to the 1/2 integral of epsilon d epsilon. So I'd have to pull that in. But that cancels out with that, so that leaves a 3 m to the 1/2 if I pull that out. But I actually want it to cancel, shouldn't I? Shouldn't it cancel? Because the end result that they get, is as d epsilon g epsilon over that. So everything should just cancel out. But I'm not getting the cancellation. I'm not getting that. I don't know, where is that pi squared? How does that pi squared canceling itself out? Like how's this pi squared then turning into nothing? Yeah, I get pi squared there as well. Why is there no pi squared there? There should be a pi squared. K squared over pi squared dk. Where is it getting that from, man? I'm not able to solve this right now, dude. What the hell is going on? My brain. I should be able to solve this though. Come on, it's not that insane. Like this should be fairly trivial to do, right? N is equal to v integral of g epsilon dk. In this case, 2v over 2 pi cubed integral of 4 pi k squared dk. Right? Then we're given epsilon h bar squared k squared over 2m. I guess we don't even have to do that. Because epsilon is equal to a k to the b. D epsilon is going to be equal to b a k b minus 1 dk. Yeah, I guess the key comes with like if you just know how to do this change of variable, then you should be good. But how do you do that change of variable? Let's just explicitly try to work out the change of variable, man. Epsilon is equal to freaking h bar squared k squared over 2m, right? So an epsilon 2m over h bar squared is equal to k squared, right? And we also get that d epsilon is going to be equal to 2, so that cancels out. So h bar squared over m k dk, right? And then we have that dk is just going to be equal to mde over h bar squared k. But we want to express dk fully in terms of epsilon. So then since k is equal to that, so it's mde over h bar squared times square root of epsilon 2m over h bar squared. Let's ask Wolfram Alpha to reduce this. Am I signed in? Can I sign in? Is it going to leak all my information? Bruh. I know I'm logged in on Google Chrome, right? Yes, I am. Okay, so I'm gonna do some off-screen mining. So m over h squared times square root of say epsilon is n 2m over h squared. Simplify this, please. Simplify. The fuck? It's not that simplified, is it? M over, I guess the h bar squared completely does not cancel out yet, actually. Pull it out, so then that's just h bar squared times h bar, which is then h bar to the cubed. I'm hearing voices behind me, dude. I'm freaking tweaking. Like, I don't know how you can do this change of variable and it just turns out fine. But anyway, let's try plugging in 2v over 2 pi cubed integral of 4 pi k squared is epsilon 2m over h bar squared. And then dk is m over h bar squared k d epsilon. So now we have it in terms of just epsilon, but we don't yet. Equal to 2v over 8 pi cubed times 4 pi times 2m squared times 1 over h bar to the 4 integral of epsilon over k d epsilon. Four pi cancels that, so that leaves 4 or 2 pi squared. Then those twos cancel out. So it's just m squared, pi squared. So it's 2v over pi squared, m squared times 1 over h bar to the 4. Wait, how did we get 2 terms of epsilon? No, it's 4 pi k squared. K squared is epsilon 2m over h bar squared. Oh, because we inserted the dk. That's where you get the h bar to the 4. Integral of epsilon times 1 over yeah, I don't know if there's a way to freaking I don't know. I guess you know what? I guess we just memorize it. I guess you just take this as is. Maybe the book did this. Surely the book did this at some point. Although my hopes are not high. Maybe the GSI did this in a discussion in the week. Okay, here that is. Do they change integrals? K squared is equal to that. Dk over d epsilon is equal to that, yes? Yeah, you get some whack shit like this. Oh, I don't know. Anyway, I guess we just have this. Okay, so let's just not try to, let's just remember that n is equal to v integral of g of e gk d n is equal to v integral gk or d cubed k, the wave vector, which is just v g of k d k. Right, where is that? Where was it? Oh my god, what the fuck is going on with my nose, dude? Oh, it hurts like hell right now. I just realized I don't have the... I can just put the camera back up. Because you guys can't even see what I'm working on, so there's no point. Jesus, man. In order to change variables in interval k squared, blah, 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 blah. What was it before? Something like this. Yeah, it was v over 2 pi to the d dd. Oh my god. Okay. N is equal to v over 2 pi to the d integral of d dk. Right? I finished all my tea. God damn it. Oh, 2 comes from the electron spin degeneracy. Because of the Pauli exclusion principle. That's kind of important. So then I guess, so I fucking guess 8 pi cubed times 4 pi integral of k squared dk, which is then just going to be equal to 4. That's 2. Then those 2 cancel out. That pi cancels out to a squared. So it's v over pi squared integral of k squared dk. And then I guess you just know that this is equal to v integral of g of epsilon d epsilon. I guess you just have to know this. Yeah, you just have to know this. I don't know how are you supposed to know that? That's another question to ask. For 3, how do you know that n is equal to pi squared integral dk k squared is equal to omega integral g of epsilon d epsilon? When I try to explicitly change variables, I get some long answer, not this, ... Okay. Okay, now we can just kind of work it out. I guess if we just start from that, and then you can just work it out. So that's just something we're gonna have to memorize, and let's test that we memorize it by just writing it down. N is equal to the summation of k states times 2, because electrons can occupy 2 spin states. So this is just going to be equal to V. I guess we can just write omega. Omega integral omega over 2 pi cubed integral of gk dk, which is going to be equal to omega over 8 pi cubed integral of 4 pi k squared dk, which is going to be equal to omega over pi squared integral of k squared dk, which is equal to somehow omega integral of g of e dE. And now this problem is probably going to become a whole lot easier. If I had to predict, if I had to guess, it's probably going to become a whole lot easier. Let's not look at that. So now we have that our epsilon. This is really boring without like seeing it. I'm going to get my iPad. This is boring without being able to see it. It'd be more fun if you guys could see it. My iPad is actually in this room. Is the iPad in the room with us right now? Yes. Will you believe it? It actually is. Ba-ba-da-ba. I don't know what the fuck those people are doing, but... Okay. The iPad is indeed in the room with us right now, and I can actually plug it in to show you what I'm doing, because I did this whole nice little fancy thing. You'll see. Once I plug it in, you'll see what the fancy thing I've done was. Plug it in. Plug. There we go. It should be showing up on the screen sometime soon. Hopefully. There it is. Look at that, baby. Look at that. Now you can see what exactly I'm doing. Let's do some miscellaneous stuff. Okay. Now this is basically what I had, right? What I had was... So I have n is equal to... So this is like the starting point. K times 2. Which is then just going to be equal to... I guess I can zoom in more on this. But then it's quite big. All we can do is we can just make this a little bit bigger. Tiny bit. There we go. Now you should be able to see this, no problem. If not, if you can't see this, up your resolution, okay, to 1080p, because I'm streaming in 1080p. All right, but... So basically, what's going to happen is n is equal to this. And so now you should know, so n in general is equal to omega over 2 pi cubed integral of g k dk, right? This is generally what it is. So with a 2, now that's going to be 2 omega over 2 pi cubed integral of g. Well, this integral, technically, I don't think this is correct. But whatever, if you do like a triple integral, okay, you can reduce it down to one integral in terms of k. It'll just give you 4 pi k squared dk, right? So this is going to be equal to 2 omega over 8 pi cubed. If you expand that out, times 4 pi integral of k squared dk. The 4 pi cancels out with this, gives us a 2, gives us a squared there. That 2 cancels out with that. So then you're left with omega over pi squared integral of k squared dk, right? And so now if you change variables, you're just supposed to know, this is like a question, I don't know how, but you're just supposed to know that this is equal to omega g epsilon d epsilon if you change variables. That's the thing I spent a long time trying to figure out. How do you know that it's equal to that? I have no idea. But anyway, moving along. So now we have this. So we have omega over pi squared integral of k squared dk is equal to omega integral of g of epsilon d epsilon. And we're given in the problem statement, right, that this is what epsilon is. So we're given what epsilon is. Let's put it all the way over here. So we're given what g of epsilon is, and we're given what epsilon is. So epsilon is equal to a k to the b, right? Yep. And then, so then with this, we can figure out what d epsilon is by just taking the derivative of k. So derivative of k is going to give us a b that's over here, a k b to the minus 1 dk, right? So then that's what d of epsilon is. And we know what g of epsilon is because it's given by the problem. It's given as 3 epsilon to the 5 over 4 pi squared gamma cubed, right? So now we just plug that in. So plugging this in, omega over pi squared. I think because the volume is on both sides, we can cancel out this omega. So we just have 1 over pi squared integral of k squared dk is equal to integral of g epsilon, which is 3 epsilon 5 over 4 pi squared gamma cubed times d epsilon, which is b minus 1 dk. Right, that's what that is. Shit, now we have a k and an epsilon. Wait, how do we reconcile that? Now, what the fuck do we do now? Yeah, wait, what do we do now? I guess we have two expressions in terms of dk, right? No. Yeah, this is the point that I'm at. But I didn't, wait. So I guess I should express epsilon in terms of k. Oh. Brain moment, okay? What we can do is just have this, so 1 over pi squared, integral of k squared dk is equal to the integral of 3, and then we just express epsilon. Epsilon is already expressed in terms of k, all the way up here, okay? It's already expressed in terms of k, so we just plug that in. A k to the b to the 5/4 over 4 pi squared gamma cubed b a k b minus 1 dk, right? So now we have all of this. We got all of this junk. I don't know why they don't have the integral sign here. Why'd they just drop it? And I guess if you look at this, there's a pi squared on both sides, so you can cancel that out. So now you have integral of k squared dk is equal to the integral 3ak to the b to the 5/4 gamma cubed b a k b minus 1 dk. Shit, that's a lot. It's a lot of stuff. So I guess we do just expand this. So let's simplify this even more, I guess. 3 akb to the 5/4. That's going to be a to the 5/4, k to the b, some exponent to the exponent you multiply. So it's going to be b5/4 over 4 gamma cubed times b a k to the b minus 1. So if you have k to the b5/4 times k to the b minus 1, then you can just take the exponents. How do you deal with this again? K, when you're multiplying exponents together, I think you just multiply together, right? Because it's the same base. So you have b squared. So in this case, b5/4. So 5/4b times b minus 1. It's going to be 5/4b squared minus 5/4. So that's the k that you have now. So it's going to be 3a to the 5/4 k 5 over 4 b squared minus 5 over 4 times ba all over 4 gamma cubed. A times that is going to be a squared. A times that. I guess you add exponents then? Do you add it? It's 9 over 4. It's 3a to the 9 over 4b. K b over 4 minus 1. Oh, I think you add it. Oh, my algebra. Oh, my algebra. Oh, my algebra. Yeah, I think you add it. You don't multiply it. So it's b 5 over 4 plus b minus 1, which I guess would just be b to the 5 over 4 plus b minus 1, which is then b 4 over 4, so 5 plus 4 is 9. Yeah, so that's 9 over 4 minus 1. So that's going to just be k to the b. Okay, so then you get integral of 3. So an a to the 5 over 4 plus 1, that's going to be a to the 9 over 4. K b 9 over 4 minus 1 times b all over 4 gamma cubed, and this, remember, is equal to k squared dk. And now, so now the key thing to see here is that we have a k squared and we have a k to some exponent here, and all this other junk, we can just consider this, like we can just toss it to the side. So with this, now what we can get is the relationship that k squared is going to be equal to k to the b 9 over 4 minus 1. And so then you can just say 2 is equal to b 9 over 4 minus 1. And now you can solve in terms of b. So 3 is equal to b 9 over 4. So then 3 times 4 over 9 is going to be equal to b. So that cancels out to give you 3. So then 4/3 is equal to b. So b is equal to 4/3. Now you have that. Now we can plug that back in to this garbage, right? So then now we had k squared is equal to k squared dk is equal to the integral of, what is this? 3a to the 9 over 4 k to the 4 over 3 minus 1 times 4 over 3 all over 4 gamma cubed, right? This is what we have now. That's our expression. So 3a to the 9 over 4, k to the 4 over 3 minus 1 is going to be 1/3, k to the 1/3 now. Is that true? B is equal to 4 over 3, right? Yes. Okay, b is equal to 4 over 3. Times, so the 4's cancel out, so then that would just give us 3 gamma cubed. And now those cancel out, and so now we just have shit. Yeah, I'm pretty sure there's a dk here. So now we just have a to the 9 over 4 k 1/3 over gamma cubed is equal to k squared dk. So now we have this. How would we solve for a now? A now, a now. A now, a now. How'd they get the 4? What the fuck? How'd you get this? You still have the coefficients in front of k? I guess before you reduce it, okay, so you still have b. Yeah, wait, no, so you do get this. Yeah, a to the 9 over 4 over gamma cubed. That's a 3, gamma cubed. Okay. Oh, okay. So you have k squared dk is equal to the integral of a to the 9 over 4 over gamma cubed times k to the 1/3 dk. So you have k. So you have k here, a k here, and then you have something here, and you have the invisible coefficient of 1. There's an invisible coefficient of 1. Didn't you know? You didn't know that? So now you can just say from this, you can get 1 is equal to a to the 9 over 4 over gamma cubed. So then gamma cubed is equal to a to the 9 over 4. So I think you take the exponential or logarithm. I think you take the natural log. Wait. Yeah, you take the natural log, right? Right? Take the natural log because then that'll bring the power down and then you'll have ln of a. And then you can exponentiate after. So then now let's move that over. So ln of gamma cubed over 9 over 4 is equal to ln of a. And then exponentiating, you get gamma cubed over 9 times 4 is equal to a. So this is not at all what I got. Wait, how do you do this? Can't believe I'm forgetting these techniques. I should be able to derive these techniques though. Like in an exam, I would try my best to derive it. Wouldn't say I would succeed, but solve for x, where we have z cubed is equal to x to the 9 over 4. Blah, 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 blah. What's the step-by-step solution? You raise both sides by the power of 4, and then you take the 9th root? What the fuck? What the fuck? Jesus, man, someone's working behind me. How the hell do you do this? Do you guys see this guy behind me? He's at my window. You can't quite see it, but there's someone behind me in my window. It's uncomfortable. Now I feel like I'm being watched. But anyway, apparently, so if you take the 4th power of both of these, so raise this to the 4th, raise this to the 4th, so then you get a to the 9, so you go to the gamma to the 12. And then now what do you do? Raise it to the 1 over 9? So you raise this to the 1 over 9, raise this to the 1 over 9. You have gamma to the 12 over 9 is equal to a. Oh. Yeah, I guess that makes sense. Yeah, there's no fancy tricks involved. And then 12 over 9, you know this. What goes into the 9? 3. What goes into both 12 and 9? 3. And that goes in there. So gamma 4 over 3 is equal to a. So now you have your a value. Right? So now you know epsilon is equal to a k to the b. So it's just gamma to the 4 over 3 k to the 4/3. Yeah. So it's equal to gamma k to the 4/3. That's your answer. Bob's your uncle. Right. Okay. All that. Not bad. So these are the important steps though. Remember this. Electrons occupy 2 spin states because they're fermions and that's how they be. And then that's another formula to remember. Linked to this formula. And you also just have to remember this is equal to n. I don't know how, but I don't know. So those are the things, those are the key things that you just have to know. But okay. That makes sense. Okay. Weird guy is gone from my window now. He's still somewhere there, but oh my god. Alright, I'm gonna go use the bathroom real quick, and then we will be back. But just look at this crowning achievement. We did all this. We got it. We got it. But these are like the key formulas. These ones right here, these are the key formulas. So we just have to kind of know. Okay. Okie dokie. Number 4 is the last one. 4B is a pretty hard one. But 4B will be covered in discussion today at 6 p.m. Right now it's 2:47. It's basically 3 p.m. Dude, I wish I had these fun fucking classes, man. God damn it. Oh my god. Okay. Break taken. Now let's go on to number 4. In the context of the Debye model, describe the difference between a longitudinal mode and a transverse mode. Well, if I had to guess, a longitudinal mode. What's the difference? I don't know. Longitudinal is parallel with the direction of propagation. Transverse is perpendicular to the direction of propagation. That's why light is a transverse wave, because it also because light only has transverse modes. The components of light are only transverse because there's only the E field and the B field, which are perpendicular to K, the wave vector, and they're perpendicular to each other as well. Longitudinal mode, sound is a longitudinal mode because it can move in the direction of propagation. Light can't because light remains constant. In the Debye model, a longitudinal mode is a sound wave, defined by some wave vector k, in which the atoms oscillate in the direction of the propagating wave. A transverse mode involves atomic oscillations perpendicular to k. Yeah, that's pretty much it. That's pretty much what it is. Now, this is a hard problem. I don't want to do this. I don't want to do this, man. I'm thinking, what should I do after this? Should I look at the homeworks? I should probably look at the homeworks, right? I would think. Look at the solutions to the homeworks. Just see if I kind of understand it. There's too much, though. Holy shit. Look at this. Look at this. Look at this bullshit. Bro, this is fucking crazy. This is fucking crazy, boy. Oh my god. I'm not looking at the homeworks, bro. Oh no. Yeah, I should also just ask her how much what are the formulas we should know? What formulas should we just know? Okay, anyway. In real solids, the sound speed of a longitudinal mode VL is generally not equal to that of the transverse mode. Find an expression for the Debye frequency in this case. It may help to derive the usual Debye frequency first. I don't know how to do that. No, listen up. I don't know how to do that. Debye frequency? I know Debye frequency is omega is equal to V K, where V is the velocity, it's a vector. K is also a vector in that case, but like I don't know how you derive it. End of class problem. Which of these problems was easiest for you? Which was the most challenging? Easiest is probably number 1, just because it's pure conceptual. The most challenging? Maybe 4B. It makes sense. 3N. That makes sense. Oh shit. Wait, you can use 1/2 N. I don't know. I feel like I need to relax for a moment. I've been streaming for like 2.5 hours non-stop. I need to like chill for like an hour. Should I eat something? I don't know if I should eat anything. I've eaten quite a bit. Enough. I've eaten quite enough. I think I'm just gonna chill. I'm gonna chill. How long is the solution for this? It's not too long, actually. You know what? Let's try it. Let's try it out. Let's try it out. So we have our trusty old formula where N is equal to omega integral of G k dk, right? This is our trusty old formula. 4 pi k squared dk. You always start off with this, don't you? You always start off with this. So this is omega over 8 pi squared. The 4 pi, if they cancel out, that will give you 2. That will give you just a, whoops, pi cubed. So that will give you a squared, pi squared, integral of k squared dk, where this is 0 to kf, right? And because, but now 3 modes, so we have 3n, which is equal to omega over 2 pi squared, integral k squared dk, kf 0, or n. Now we have omega over 6 pi squared, right? Should be that. Why is there just a 3 here? Oh, I guess the way, oh. No, the way that, no. The way that you think about it is now you have 3. So you take this times 3, this times 3, which is going to be equal to 3n, 3 omega over 2 pi squared, integral k squared dk 0 to kf. But now you express it in terms of omega. Oh, so you do a variable change. You do change a variable. So you know omega is equal to vk, right? So then k is equal to omega over v. Wow. Yeah. Can you just change the yeah, you can just change it to w. You can just change it to omega. You can just change it to omega. Just change it to omega. So now k squared is omega squared over v squared, velocity, dk. Oh, now we need to know what dk is. dk is going to be equal to d omega. It's d omega. 1 over v d omega. Right? Yeah, because you have a v cubed. Yeah, that's what it is. So it's 3 omega over 2 pi squared dk, integral of 0 omega to omega squared over v squared 1 over v d omega. Oh my god, so we pull that out, times 1 over v cubed, integral of 0 to omega of omega squared d omega. Oh my god. And then we can just do that integral from 0 from 0 to omega 3 pi over 2 pi squared v velocity cubed, integral omega squared, that's going to be omega cubed over 3, integrated from 0 to omega, which is just going to be that. So that's what we get. Boom. So those 3's cancel out though, so now we have omega 2 pi squared velocity cubed. That's what we have, right? Omega cubed. That's a 3. It just looked like a 2. Okay. 2 pi squared v cubed. Yes. By the way, if I look down here, I can't. My solutions are right here. Okay. I'm not looking at that when I'm looking down here. Okay. So now we have this. So now we have 3n. Now where would we work from here? Express everything in terms of omega, I guess? Little omega? That would give us that omega cubed is going to be equal to 3 times 2. We just do 3n 2 pi squared v cubed over omega. It's equal to that. Now what would we do with that? I don't know. Wait, what is even the question? Yeah, okay, so we do that. Yeah. It's gonna be equal to the cubed root of 6n pi squared v cubed over omega. we can pull out the v, so we just have v cube root of 6n pi squared over omega. Where'd the omega go, though? Why'd you just get rid of the omega? Where'd that go? Huh? 6 pi squared n, big N. So what they did, why'd you express big N? So n, so we know that small n is equal to n over omega, n over v, which in this case is our omega, right? So that gives you velocity cube root of 6 n pi squared. I don't know why you would do that, though. Why would you need to do that? Okay, now you have the Debye frequency, but your v's are separate. So you have to rewrite it as an expression of a sum of two things. So this is finding the usual Debye frequency. Wait, no, we didn't. Oh, so this is the usual. So all this work is just for... This is the usual. Right? But now we want to find the real. So I guess it was a good exercise just to find the usual one. I guess just to do it. But for the real one, right? For the real one, what we would need to do is, I guess when we reach this point, we'd have to split this point into two, I think. Right? So we have 3n is equal to 3 omega over 2 pi squared, 0 to omega, omega squared over, this is VL dk. Or I guess this point, more accurately. Whoopsies, undo a lot of that. It's this point that we need to split off. So that's 3n is equal to 3 omega over 2 pi squared integral of omega squared over v cubed d omega, right? Yes. Now this will just become a sum of VL cubed d omega plus, this is going to be separate from this, integral of omega squared over v t cubed d omega, right? Yeah, it would be this, yeah. Except we got the modes wrong. Now, why did we get that wrong? Well, one thing that we have to remember is that longitudinal waves have one mode and transverse waves have two modes, right? So longitudinal waves, if your wave is propagating in the z direction, your longitudinal wave can move along the z-axis only. For a transverse wave, if we're thinking about 3D, since the z-axis is the direction of propagation, that only leaves us with the x and y-axis to fiddle around with. And so transverse waves can move in the x and y-axis, so that's two modes. So then your three modes are now split in. So this coefficient here, so the important thing is that you have one mode here for longitudinal and two modes here, since those will add up to give you three modes. Okay, and so that will just give you omega over 2 pi squared. Same thing that we did before, omega cubed. That would give you 6 over VL cubed plus 2 omega, so that cancels each other out. So you just have omega over pi squared, omega cubed. That's over 3 now, over VT3, right? It's T, so this is just going to be equal to what? Omega over 3 pi squared, and then with an omega cubed, you can factor that out, and then you just have a factor of what? 1/2? 1 over 2 VL cubed. So you have a factor of 1/2, 1 over VL cubed plus 1 over VT cubed. Is that it? Yeah, right? Yeah. I don't know why they included the 2 in there, but yeah. Yeah, and then, okay, yes. Yeah, and then you solve for omega, so that's going to be what? 3 times 3, 3, 6, 9. It's going to be 9 times 2 is going to be 18. So it's going to be like 18, yeah. So then it'll be like 18 pi squared over omega VL cubed plus VT cubed, right? Some factor of that up in there, up in that shiz, right? Yeah. Remember, this is times n cubed root. Yeah, just gonna be omega cubed root. I don't think this step is necessary, but yeah, you can just express it in terms of small n, because yeah, you can just say n is equal to n over omega. Okay, that's that. You know what? Okay. So that makes sense, how you would get that. My algebra's a little bit wrong, but who cares, man? We're not worrying about over all these fucking constants. What does it look like? I'm born in Constantinople? I don't care about them constants. Ha ha ha. Ha ha ha. Anyways, that's that, man. That is that. Yeah. 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 Okay. That's that. I guess we'll take a break until 4. Come back at 4 to try to read some more. And then at 6 is our class. So yeah. 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 Okay. Let's move all this back to this screen. I don't know if I have time to look back on the homeworks, bro. So, I don't know. So, that's a thing. I think my intense studying, I didn't quite do it for chapters 2. For chapter 2, I think I did it for chapter 3, though. I think I did the intense studying for chapter 3, though. I think. But chapter 3 is still just a little bit confusing, but... basically what I'm saying is, I think my intense studying, my relentless studying of... what am I trying to say? Yeah, I think my relentless studying of the book, when I just read the textbook the first time, I think just reading it well the first time and like using ChatGPT to parse through how badly the book is written. But I think going through that process helps a lot in terms of like actually thinking about like what the hell's going on. So seems like the midterm is going to be easy. It seems like you just need to like start off with this. Basically, like this is just what you start off with. Basically. Right? You just do that. You just use that formula. And if I do that in the midterm, you know, like maybe I'll forget to like, oh, include this factor of 3 that's like right here in the middle. Maybe I'll like, oh, I forgot to include that factor of 3 there or something. But whatever. Like I'll still have like most of the working pretty much there. So it'll just be off by like 1 coefficient, but whatever. So seems like once you have this formula, you can do anything. Just express things in terms of k, take derivatives, blah, blah, blah. Also, just somehow remember this relationship. And then it just seems like it's going to be fine. So yeah, whatever. I'm not going to waste my free time any longer explaining to you goobers what's going on. So iPad disconnected. Take the cable. Roll it up. And that's pretty much it. That's all she wrote. I am now going to probably play Call of Duty while listening to a podcast. Okay, the signature, the staple. But anyway, peace out.